NASA STEM team from Phoenix College. My name is Eunice Lopez. I am the team lead, and my major is software engineering.
My name is Evan Martinez. I was on the networking and software systems, and I am a computer science major.
Jessica France, signals and radio systems, mechanical engineering major.
Christopher Yergel, mechanics and materials. I'm an aerospace engineering major.
Brian Loyal, electrical planning, electrical engineering.
Isaio Diarte, I was working on the electrical systems. I'm an electrical engineering major.
Modesta Juarez, I was also working on the electrical systems, and I am a computer science major.
Jackie Salazar, science and research, and chemical engineering major.
For our project, we had three major goals. The first goal was to live stream video from our payload during flight. The second goal was to build housing that would protect all of our hardware during launch and on descent. And the final goal was to gather atmospheric data for scientific analysis. For the fall launch, we attempted but were not able to live stream video. After analyzing our results, we redesigned and enhanced our systems. So for this presentation, we will talk about the implementation, the design, and the results of each goal for our spring launch. So to start off, we have the video system. For our first goal to live stream video, we had a video system that was comprised of three subsystems. The first was the video transmission system on the payload. This transmitted our live feed to the ground. Our ground station video system then received this transmission feed and uploaded it to YouTube. Our ground station rotor system maintained our antenna pointed in the direction of the balloon. To accomplish this, we used software that compared APRS packets to ground station data, sensor data. It then calculated and sent correction commands to this rotor system to maintain the antenna pointed in the direction of the balloon. So what we're going to do next is we're going to break down each subsystem. And to start off, we have the video transmission system on the payload.
So the video transmission system was comprised of the following components on board the payload. It was comprised of the Raspberry Pi camera, the Raspberry Pi, the Rocket M5AC wireless transceiver, and the two 5.8 gigahertz wireless Wi-Fi antennas. So video processing worked like this on the payload. So first, we acquired the video using Raspberry, and from Raspberry we took recordings locally in 10-minute chunks, and we saved that recording for redundancy. From there, we passed the video through the VLC player, or video LAN player, which produced a RTS feed stream known as the real-time streaming protocol. From there, the video left our payload on the Rocket M5, which was transmitted down to the ground. The hardware for our ground station system included another Ubiquiti Rocket M5AC wireless transceiver and a Rocket M5 Rocket Dish lightweight series dish antenna. And then the video streaming process on the ground started at the Rocket Dish, where we acquired the signal. And then it was subsequently processed by the Rocket M5, where it was digitized in a format that we could see. And then we processed the video on the VLC player, where we were able to decode the video and get an MP4 file out of it. And we streamed that MP4 file using OBS.
In order to improve communications between our ground station and the payload, we constructed a rotor system which actively tracks the flight of the balloon. This rotor system automatically adjusts the angle of the ground station dish antenna to within 9 degrees of the payload, which we calculated to be optimal for signal strength during testing. The hardware for this rotor system includes a magnetometer sensor for heading, a 9DOF sensor for elevation, a GPS sensor, and 2 servo gearboxes used to control the antenna, where one is used to adjust heading and the other is used to adjust This tracking system starts with a Python script that pulls APRS packets from the APRS IS servers. These packets provide us with the balloon's latitude, longitude, and elevation. A GPS sensor then provides the latitude, longitude, and elevation of our ground station to the Python script. The script then takes the two and calculates our target heading and elevation. This target heading and elevation is then sent to the Arduino. The Arduino determines the antenna's current heading and elevation from sensors mounted on the rotor and compares it to the target heading and elevation sent from the Python script. It calculates the shortest route to the target path and sends the commands to the servos. These servos, directed by the Arduino, continuously adjust the antenna's position to match the last target position received.
With the implementation of these three subsystems, we were able to accomplish a video connection for 20.8 miles, a data connection for 21.5 miles, and we did have a delay in our video transmission, and this was due to transmission, video processing, and upload delays. We were able to successfully run our rotor controller system off of APRS packets for our fall launch. For our spring launch, we were able to control the rotor, but we had to provide it with some required values. For our next slide, we have a 20-second video clip from our live stream on YouTube Live. We were able to live stream our launch by positioning our ground station about 500 feet from the launch site. We are able to take advantage of the APRS packets at about 758 feet. Until we reached this elevation, we were manually controlling the rotor.
Our second main goal was to build a housing that would protect all of our components during the flight. Here's the rendering, and as you can see on the table, the real thing. For this, we chose carbon fiber. It has a great strength to weight ratio and also excellent impact resistance. So we began building this with a wood mold. We encased that in 3 layers of carbon fiber, and it was hardened with resin under vacuum. Our lightweight payload allowed for secure mounting of all of our components, and upon recovery, we found nothing at all damaged. We also used Kevlar cord suspension system in favor of a fiberglass rod, which further reduced our weight, and also removing the rod helped with the severity of impacts with other payloads. As you can see on the front, we have a key switch to turn the payload on and off, also 2 power LED indicators, one for our battery and one for the Raspberry Pi. The main disadvantage to this type of design was just lack of insulation. This was partly due to carbon fiber, which is only about 3 millimeters thick. Also on the inside, we use low-density foam to protect our components, which is also not very insulative. So the battery, which is mounted here on one of the legs, it got very cold, and it reached its lower operating temperature, caused a brief disruption in power, and that disruption is also reflected in the data we gathered.
The data from our constraint propelling system was done through an SD card. This system included a ground temperature sensor, 2 orientation sensors, the NP6050 and the LS1030, a barometer which estimates altitude based on pressure and temperature readings. These sensors were soldered on a shield connected to an Arduino. Based on the data, temperature were rapidly decreasing before we lost power. We lost power at this point when the temperature reached -30 degrees Celsius, but our system turned on at this point when the temperature reached 28 degrees Celsius. If we compare and overlay these charts, which are temperature charts, to the accelerometer graph, we can verify that we lost power during this thing. we can see an increase in acceleration and altitude axis, which indicates loss of altitude and a change in acceleration.
The payload also included a power data distribution board that allows us to use one power source for our electrical systems. It was an integral component to achieve our 3 main goals this semester. And it reduced the points of failure by eliminating unnecessary components and wiring, which also helped reduce the weight.
Okay, so what we have here is the power distribution system that we created. We had a 7.4 volt LiPo battery that went into two separate systems, two separate converters. One of the converters was a buck boost that generated a 5 volt output to power the Raspberry Pi and the Arduino. The other converter was used to boost up the voltage to 12 volts to power the Ubiquiti transceiver. And we also had data lines coming from the Raspberry Pi's Ethernet port and going into an RJ45 on the board. And that RJ45 had connections to the data connections on the Ubiquiti modem. This setup allowed us to power all of our subsystems and created all the data connections that we required.
One of the biggest challenges on this project to build a system like this was building a housing that would contain all the components that still was within that 3-pound weight limit. Even after reducing unnecessary wiring, building the custom power distribution board here, choosing carbon fiber and also using Kevlar, we were just under the weight limit. We were at 2.97 pounds. Our heaviest component within the payload was the battery. That was 0.69 pounds. The payload itself was 1.3 pounds, and all of the other components each were no more than 0.21 pounds.
We intend to share our results and research with future teams to improve this system. We would like to thank everyone that makes this program possible and would like to give a special thanks to Arizona Space Grant Consortium, Arizona Near Space Research, our faculty mentor, Ernest Beicanya, and our science advisor, Dr. Edong. Thank you. Any questions?